some of the weak gravity conjectures, and the rest of the talk is going to be devoted to explaining how this works out, and this is going to lead us to black holes and BPS states. So first of all, we've seen these conjectures a number of times already in this conference. The Swampland distance conjecture says that when you go out some far distance in moduli space, you get this tower of exponentially light particles. And the weak gravity conjecture says that in any abelian gauge theory coupled to gravity, you need a particle which is super extremal in this sense. Note that I'm going to use the word super extremal throughout the talk to include things that are exactly extremal. A number of strong forms of the weak gravity conjecture have become popular in the last couple of years, and some of them, which are all of the same flavor, are the tower weak gravity conjecture, which says that you don't just have a single super extremal particle, but rather at an infinite number of sites in the charge lattice. The sublattice weak gravity conjecture is a strictly stronger statement, which says that these charges should fill out a sublattice of the charge lattice. And finally, you could have imagined that every site in the lattice should have a super extremal particle, but this seems to have counterexamples. I'm not going to go into the rationale behind these strong forms. For that, I would refer you to the talk that I gave at the Simons workshop this summer, which you can find online. But I do want to say that the main motivation, and I think the strongest argument for these tower and sublattice weak gravity conjectures, comes from considering the behavior of the weak gravity conjecture under Kaluza-Klein reduction on a circle. So if you perform such a reduction and you want the lower d-dimensional theory to satisfy the weak gravity conjecture, you need to impose something like the tower or sublattice weak gravity conjecture in one dimension higher. And so it's important to note that the weak gravity conjecture in d dimensions leads to these conjectures in one higher dimension. Now, the weak gravity conjecture places an upper bound on the mass of some charged particle or charged particles in your theory. The BPS bound is a sort of converse of this, in that it places a lower bound on the masses of all the particles in the theory in terms of their charges. So in particular, the BPS bound relates the mass to the central charge of the state, where the central charge depends on both the charge of the state, Qi, as well as the moduli in the theory. Now, there's many things that could be said about BPS states. These things have been extensively studied. They're very important. But the one thing I'll mention is that in some contexts, you can actually count the BPS states in a theory. So you could ask, how many BPS states are there of a given charge in a given theory? And for 4D n equals 2 theories, which come from type 2a string theory on a Calabi-Yau threefold, you can count the BPS states coming from D2 branes wrapped on 2 cycles with what are known as the Gopakumar-Vafa invariants. And the point is that these things are actually calculable in many examples. So this leads us now to what appears at first glance to look like a very serious counterexample to the tower and sublattice weak gravity conjectures, namely the conifold. So at a conifold singularity in a Calabi-Yau threefold, where we compactify type 2a on this geometry, the BPS bound becomes trivial as the two cycle shrinks to 0 size at the conifold singularity. And so what will happen here is that the mass of some charge 1 particle or particles will go to 0 as the BPS bound becomes trivial. But importantly, the conifold singularity is at finite distance in moduli space. And as we've learned from Irene's nice talk, the Swampland distance conjecture and its converse suggests that infinite distances are associated with infinite towers of states, and finite distances are not. So here it appears that we have only a finite collection of states becoming light at the conifold singularity. And indeed, if you work out the Gopakumar-Vafa invariance for this one particular famous example of a conifold, you find that indeed, for charges 2 and above in this direction in charge space, there are no BPS states at all. So there are 16 BPS states of charge 1, none for higher charges, and in fact, you see there's this entire wedge in charge space that's devoid of any BPS states. So naively, this looks like a very bad violation of the tower and sublattice weak gravity conjectures, because we're getting this, the BPS bound going to 0. We're getting a single BPS state. But as we go to this locus, there's not an infinite tower of charged states becoming light. There's only these 16. So the rest of my talk is going to be devoted to explaining to what extent this reasoning is correct and to what extent it's misleading. And this is actually going to lead us to some interesting facts about BPS states and black holes. So let's start out with the 4D conifold. At the 4D conifold locus, a gauge coupling actually does go to 0 logarithmically. And this is just simply due to the logarithmic running of the gauge coupling in 4 dimensions when we have a massless charged particle. So when the BPS states of charge 1 become massless, they're going to induce this logarithmic running. The gauge coupling is going to go to 0. And so strictly speaking, we actually do get a violation of the tower and sublattice weak gravity conjectures in 4 dimensions in the deep, deep, deep infrared. So if you look in the deep, deep, deep IR, the gauge coupling actually goes to 0, but we don't have a tower of massless states. So the weak gravity bound defined in the infrared is no longer satisfied by a tower of particles. So strictly speaking, we have a violation, but I would say that it's sort of a lame violation, because really all it's telling us is that in 4 dimensions, massless charged particles cause the gauge coupling to run to 0. The original motivation of the weak gravity conjecture dealt with charged black holes. And here, the black hole spectrum is not going to become massless. There's still going to be these massive black holes, because at higher energy scales, the gauge coupling is not going to vanish. It's only this IR effect. And so if you were to imagine, considering not the charge of the particles in the deep infrared, but rather defining the charge at the mass scale of the particles, you'd find that they satisfy this renormalized weak gravity bound. So once you sort of modify the statement to account for this logarithmic running in 4 dimensions, you see that these issues go away. It's also worth mentioning that logically, it's possible for the tower and sublattice weak gravity conjectures to be violated in 4 dimensions without contradicting any widely adhered to principles. That's because, as we saw, the weak gravity conjecture in 3 dimensions is the thing that leads to the tower and sublattice weak gravity conjecture in 4 dimensions. And in 3 dimensions, gravity is non-dynamical. It's not clear that the weak gravity conjecture in 3 dimensions should be valid, although some nice work by these authors suggests that it likely still is. The point is that in 4 dimensions, we have a couple of different excuses that we could choose from as to explain why it is that we're not having this infinite tower of massless states at the conifold singularity. But the point is that in 5 dimensions, both of these excuses break down. We no longer have this logarithmic running, and we actually think that the weak gravity conjecture should hold in 4 dimensions, which means that we really need something like these to hold in 5 dimensions. So for the rest of the talk, I'll focus on the 5D conifold. And here, actually, things work out nicely. Because at the 5D conifold locus, there is no gauge coupling that goes to 0. The only reason the gauge coupling went to 0 in 4D was because of this logarithmic running. In 5D, it stays finite, which means that we don't need an infinite tower of states to become massless in order to satisfy the weak gravity bound. Now, more generally, in 5 dimensions, it better be true that whenever we have a gauge coupling going to 0, we should see a tower, an infinite tower of states becoming massless. And by the Swampland distance conjecture, we expect that this will be accompanied by an infinite distance in moduli space. In fact, you can prove that this is the case, at least for M-theory compactifications on a Calabi-Yau threefold, up to certain regularity assumptions. Points of 0 gauge coupling are always at infinite distance. And I'll briefly sketch the proof. You can write down the prepotential in 5 dimensions as a sum over these cubic couplings. You assume a Lorentz expansion for the moduli is a function of t, where t parametrizes the path, which ends at t equals 0 at this point of zero gauge coupling. And then, by some clever manipulations, you can show that the metric behaves as 1 over t squared when the gauge kinetic term blows up. In other words, whenever some gauge coupling constant goes to 0, the metric diverges logarithmically. So this is one of the two main results of my talk. All of the clever manipulations are here in this third point, but all of the assumptions are here in the first two. So in assuming that theCijk and the Yi are positive everywhere, we're assuming that our path stays in a single chamber in Kähler moduli space, or a Kähler cone of a single geometry. Similarly here, we're making an assumption about the form of the path. So in principle, you can imagine some pathological path that ends at this point of zero gauge coupling, and if that's the case, these might break down. We're working on closing that loophole, but I think it's reasonable to assume that such a path is not going to be the shortest path to this point, in which case the result follows. Okay, so this is good. We don't have a problem at the conifold singularity. But you might say, well, even away from the conifold locus itself, it still seems like we should have an infinite tower of BPS states due to the tower and sublattice weak gravity conjecture. And yet we saw, looking at the Gopa-Kumar-Vafa invariance, that that wasn't the case. So do we have an issue with the tower and sublattice weak gravity conjecture even apart from the conifold locus? So for this, let's zoom out a little bit. And I need to remind you of an important fact that I think that we all knew at one point, but I at least somehow forgot along the way. And from talking with other people, I've found that this confusion seems to be fairly widespread. So the point is that in general, BPS bounds do not agree with black hole extremality bounds, even in theories with BPS states, even in theories in which some extremal black holes are BPS. The point is that you can have multiple U1s in your theory, and in general, in some directions in charge space, the BPS bound and the black hole extremality bound will agree. In other directions in charge space, they will not. And this is important because the weak gravity conjecture, as I've defined it, is defined relative to the black hole extremality bound, and so does not necessarily have anything to do with the BPS bound. Now, sort of the quintessential example of this comes from considering heterotic string theory on a torus. So we know heterotic string theory has this E8 times E8 gauge group. If I compactify on a torus, I can turn on some Wilson lines and break the E8 times E8 down to the U1 to the 16 Cartan. And for states that are charged under this E8 times E8 Cartan, there's this tachyonic mass shift, where the mass is given by this formula, with this -1. And as a result, the spectrum looks like this. Now, this is clearly not an example of a BPS spectrum. If this extremality bound here were a BPS bound, all of the particles would have to lie on or above it. So here, the extremality bound is not a BPS bound. On the other hand, if I consider different U1s, namely if I consider the winding and Kaluza-Klein momentum U1s, I would find that the states that are charged only under those are in fact BPS states, and if I go out far out on the charge lattice, I find BPS extremal black holes. So this is illustrating a more general phenomenon. The general story in a theory with BPS states looks like this. I've written down these two directions in charge to mass space, and you see here that the red line corresponds, the dashed blue line corresponds to the BPS bounds, which in this case are two planes in charge to mass space. So BPS states lie along these dashed blue lines, and states which do not saturate the BPS bound necessarily lie in between the two planes. So the BPS bounds are planes in this space, but black hole extremality bounds necessarily form a closed surface. So somehow you need to connect this plane to this plane with the black hole extremality bound. And in general, it's not clear what shape this will take. It could be rounded like this, it could be straight. The point is that in these directions, here and here, the BPS bound and the black hole extremality bound do not agree, whereas in these directions, here and here, they do agree. And this is what's happening in the case of the 5D conifold. And it's easy to see this. At the conifold singularity, the gauge coupling does not go to 0, which means that the black hole extremality bound is not going to go to 0, but the central charge does go to 0. So the BPS bound becomes trivial. Thus, the BPS bound and the black hole extremality bound do not agree for the conifold direction in charge space. So this leads to the interesting question of when exactly do they agree? And the answer is the second main result of my talk, which is that in supergravity language, the BPS bound and the black hole extremality bound agree for all charges for which the central charge is positive everywhere in moduli space. Or if you want to consider their antiparticles, negative. Geometrically, a way to say the same thing is that the homology class associated with this charge is contained in the intersection of the Mori cones over all phases of the geometry. And I'll explain this statement more later for those of you who aren't familiar with the terminology. So first, let me give a sketch of the proof of the supergravity statement. First of all, you can show that critical points of the central charge in 5D are all either local minima with positive central charge or local maxima with negative central charge, which you should think of corresponding to particles and antiparticles, respectively. Now, second, by Morse theory, you can argue that such local minima are necessarily global minima. And the intuition behind this is that you imagine sort of flooding the landscape, and you get these different basins of attraction around these local minima. But the point is that if you have multiple ones, then as the water rises, there will be some regions which aren't covered, and in those regions you must have critical points which are at positive central charge, which are not minima, contradicting this first point. So the conclusion is that these local minima must be global minima. So what this tells you is that either you have a global minimum at positive central charge, in which case the central charge is obviously positive everywhere. And in this case, you can work out the necessary conditions for BPS extremal black holes, and you find that they exist everywhere. So in this case, BPS extremal black holes exist, and the BPS bound is equal to the black hole extremality bound. On the other hand, if there is no such global minimum, the other possibility is that the central charge must cross 0 somewhere. And in fact, there are no critical points. So what this means is that a gradient flow in the central charge, starting from anywhere in the moduli space, is necessarily going to cross through zeta equals 0. And it turns out that this is incompatible with the conditions for a BPS extremal black hole. And so in this case, no BPS black hole solutions exist at all, and the BPS bound does not equal the black hole extremality bound. So once again, BPS equals BHE if and only if the central charge of this state is positive everywhere in moduli space. Now, to translate this to a geometric statement, I need to review some of the basic terminology and basic concepts in algebraic geometry. So a Calabi-Yau manifold X will have some collection of irreducible holomorphic curves, CI, which generate something called the Mori cone. So if I take all the positive linear combinations of their homology classes, it generates a cone in homology space. And I've drawn that here on the left. I've made up this geometry where there are these 4 irreducible curves, and you can see that they generate this cone in this space. Now, a Calabi-Yau threefold comes equipped with a Kähler form, which is a 1-1 form. And the Kähler cone is defined as all of the possible values of this Kähler form, where here the possible values are defined by saying that integrating j over one of these irreducible curves must give you a positive result. Now, for these holomorphic curves, this is precisely the volume of the curve. That's what's special about these curves, is the statement that they're calibrated with respect to the Kähler form, and this is what gives you BPS states, is this calibration condition. So the Kähler cone is therefore simply the dual of the Mori cone. And so here I've drawn, this is the dual to this cone right here. Now what I can do, starting from somewhere in Kähler moduli space, somewhere in this Kähler cone, is that I can cross one of these walls of the Kähler cone. And when I cross this wall right here, what happens is that I induce a flop transition, and I end up in the Kähler cone of a birationally equivalent Calabi-Yau X twiddle. Once again, the Mori cone of this X twiddle is simply the dual to this Kähler cone. So this guy here is the dual to this guy. Now here's the point. Given some curve, I can, or some homology class, I can write it as a linear combination of these irreducible curves, and the coefficients are simply the charges of the associated state in my theory. The statement that the central charge is positive then becomes the statement that the volume of this curve is positive. And so, if the central charge is positive everywhere in moduli space, the volume of this curve must be positive everywhere, which is the statement that this curve is inside the Mori cone in all the different phases of the geometry. Okay, so with these results, we're now in a position to revisit the example that motivated this talk. So let's look back at this conifold, and we recall that we had this collection of BPS states for most of the Mori cone, which is here the first quadrant. But we remember that there was this empty wedge, which was completely devoid of any BPS states except for these 16 of charge 1, which became light at the conifold singularity. So the point is that from this original Kähler cone, which is simply the first quadrant here, we can cross this wall, and that induces a flop. So when we go through the conifold singularity, we flop to a birationally equivalent Calabi-Yau threefold, whose Kähler cone looks like this. And if you compute the dual Mori cone to that, you get something that consists of the fourth quadrant, as well as this region here in the first quadrant. So we look then, according to our previous result, at the intersection of these two Mori cones, and the intersection is clearly just the dark blue shaded region here. Our result was that in these directions in charge space, the black hole extremality bound and the BPS bound must agree. So here, these two things agree, and therefore, superextremal states are necessarily BPS. Which means that if we're going to satisfy the sublattice and tower weak gravity conjectures, we better have this infinite tower of BPS states in these directions in charge space. And in fact, that's exactly what we saw from the Gopu-Kumar-Baffa invariance. On the other hand, we see now why this empty wedge is no longer a problem. In these directions in charge space, which are not contained in the intersection of the Mori cones of the different phases, the BPS bound and the black hole extremality bound do not agree. The BPS bound is strictly weaker, which means it's possible to have states which satisfy the weak gravity bound but are not BPS. BPS states are not required by the tower and sublattice weak gravity bound in this area. Now, of course, I can't tell for sure whether or not the states are there, because these are not BPS states, these are non-supersymmetric states, and we don't know how to compute the spectrum of those things. But given the other arguments, I think, for the tower and sublattice weak gravity conjectures, it's certainly consistent with what we're seeing here, that there are some states in here, some particles in here, which are super extremal, but not BPS. Okay, so this concludes what I wanted to say. To summarize, we've seen that there's this beautiful interplay between BPS states, Gobo-Kumar-Vafa invariance, central charges and supergravity, Calabi-Yau geometry and intersection theory, and black hole extremality bounds. And all of this conspires to ensure that the tower and sublattice weak gravity conjectures, as well as the Swampland distance conjectures, are consistent with these supersymmetric theories. It's interesting to note that, therefore, that these conjectures have interesting consequences for all of these things, for all of these different areas. And I think it's also very impressive how many different areas of high-energy physics are being tied together by these conjectures, not to mention all of these other areas that people have talked about in this workshop or will talk about in the next couple of days. So all of this goes to say that it's, I think, a very exciting time to be hiking to the Swampland, and it's a real pleasure to be able to do it with all of you. Thank you.
So you mentioned the heterotic example where we do know how to calculate the BPS, non-BPS states, at least in weak coupling. So you can't do similar thing here for some, I mean, there are some of these are dual to heterotic strings and all that. So you could at least presumably do analogous to what was done, for example, on heterotic on K3 times S1 or such things. Have you tried to?
Yeah, no, that's a great idea. That's something that we've talked about doing, is looking for a heterotic dual to some conifold example. So that's on our list of things to do, certainly.
So in this flop argument, the asymmetry between the two faces comes because you're working in a compact example in some sense. So if you think about some local conifold singularity where the two faces are symmetric, then you don't have these features. But of course, this is the regime where you decouple gravity. So you're not, you cannot apply the Swampland constants. Is this a correct point of view? Or?
Right, certainly. And it's certainly not the case that we expect to see these towers of super extremal and BPS states in a general non-gravitational theory. This is definitely a Swampland issue that requires the presence of gravity.